Part A asks us to write the first four non-zero terms in the general term of the Taylor series for e to the parentheses x minus 1 squared power about x equals 1. In order to find the Taylor series for e to the x minus 1 squared about x equals 1, we have to use the Taylor series equation, which is p sub n of x equals f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial. In this case, c is 1, so you would plug in c for 1, and it would be p sub n of x equals 1 plus x minus 1 squared plus x minus 1 to the 4th power over 2 plus x minus 1 to the 6th power over 6 plus x minus 1 to the 2n power over n factorial plus equals e to the x minus 1 squared. Part B asks us to use the Taylor series found in Part A to write the first four non-zero terms and the general term of the Taylor series for f about x equals 1. The question already gives you what the function of f is, which is f of x equals e to the x minus 1 squared power minus 1 over x minus 1 squared. In Part A, you already found what e to the x minus 1 squared is. So what you would have to do in this case is to take what you have and place it into the equation that you had now, which is f of x equals e to the x minus 1 squared minus 1 over x minus 1 squared. So when you start plugging in Part A into Part B, it will look like this. 1 plus x minus 1 squared plus x minus 1 to the 4th power over 2 plus x minus 1 to the 6th power over 6 plus x minus 1 to the 8th power over 24 plus minus 1 over x minus 1 squared. Then the ones cancel each other out, so you cross it out, and you just do the process of crossing it out and dividing where it is needed. And your answer would be 1 plus x minus 1 squared over 2 plus x minus 1 to the 4th power over 6 plus x minus 1 to the 6th power over 24 plus plus x minus 1 to the 2n power over n plus 1 factorial. Part C asks us to use the ratio test to find the interval of convergence for the Taylor series found in Part B. In order to solve this, you must know the ratio test equation, which is the limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n is less than 1. So using the general term from part B, which is x minus 1 to the 2n power over n plus 1 factorial, you would factor it into the equation. So it would look like this. Limit as n approaches infinity of x minus 1 to the 2n plus 2 power over n plus 2 factorial all over x minus 1 to the 2n power over n plus 1 factorial, all in absolute value. This equals the limit as n approaches infinity, absolute value, of x minus 1 to 2n plus 2 power over n plus 2 factorial times the reciprocal, which would be n plus 1 factorial over x minus 1 to the 2n power, all in absolute value. This equals the limit as n approaches infinity of n plus 1 factorial over n plus 2 factorial times x minus 1 squared. This then equals the limit as x minus 1 squared over n plus 2, which equals 0. This is because when you plug in infinity for n, you have a small number over a big number. Therefore, the interval of convergence is parentheses negative infinity, comma, positive infinity, close parentheses. Part D asks us to use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. In order to solve this question, you have to find f double prime of x. F double prime of x equals 0 plus 2 times x minus 1 over 2 plus 4 parentheses x minus 1 to the third power over 6. And when you simplify, you get 2 over 3 plus 2n parentheses 2n minus 1 over n plus 1 factorial. So your answer would be f double prime of x equals 1 plus x minus 1 plus 2/3 x minus 1 to the third power over 3 plus 2n parentheses 2n minus 1 over n plus 1 factorial. Now your final answer would start looking like 1 plus 4 times 3 over 6 parentheses x minus 1 squared plus 6 times 5 over 24 parentheses x minus 1 to the fourth power plus plus 2n parentheses 2n minus 1 over n plus 1 factorial times x minus 1 to the 2n minus 2 factorial plus . This is because every term of this series is non-negative, so f double prime of x is greater than or equal to 0 for all x's. Therefore, the graph of f has no point of inflection.